So today I will hand it over now to Erhan.
Thank you, Loisa. Thank you, everybody, for joining. I will start sharing my screen so you can see my slides. Can you guys see my slides? All right. Yeah, so today's topic is disaster decision making, where we focus on integrated prediction and optimization for resilience planning. You know, at least just as a way of introducing, you know, the topic, you know, my research is based on, let me see if I can, here you go. My research is focused on advanced model-based decision making. Some folks call it decision analytics, meaning that we focus on how we can make our decisions based on models, data, and algorithms. That's the main question. Here we apply such models and methods to disaster decision making. So today we focus on hurricanes and other heavy rainfall events, particularly floods as disasters, but we can apply these methods to other disasters and situations. My main disaster, like I said, will be hurricanes, but it could be other extreme events like winter storms and whatnot, as we will see later when I talk about what we do. We can also talk about the different settings, like infrastructures or problem domains. And our main focus will be power grid, but it could be other types of infrastructures that might be dealing with a disaster also. So with that in mind, I'll start. Here you go. So hurricanes impact, you know, quite a bit. You know, when they hit the land, right? Infrastructures, like I was saying, power grid, they are affected big time. You lose power. You know, the flooded substations and down power lines are always in the pictures. I share some of them in here from Hurricane Harvey. IT infrastructure, road network, transportation infrastructure, healthcare, hospitals and nursing homes, they are impacted. Supply chains, right? I put a couple of them in here. They are impacted by hurricanes. And of course, people are impacted, right? And sometimes we need housing for people who are impacted. And sometimes when the hurricane is big or intense, we have cascading impacts, right? One after another, one infrastructure impacting another infrastructure, and then eventually maybe people and communities. So to deal with this kind of problem, you know, there's a well-defined, actually relatively well-defined framework. People call this resilience decision-making cycle. This one is basically about, you know, what you should do before, during, and after the disaster. So well before the event, we try to mitigate. We try to harden our infrastructure and basically the systems such that we hold up against disasters. That is called mitigation, which is basically you do it well before, right? And you're not really preparing for a specific event for mitigation. Just before an impending event, you try to prepare. You try to do something preventative before the event and brace yourself for a specific event. During the event, right, you try to respond with emergency operations and maybe even rescues. And after the event, you try to recover as quickly as possible. You try to go back to normalcy as quickly as possible. Overall, this resilience decision-making cycle, you know, we see it in action, you know, before every hurricane or even between hurricane seasons sometimes, mainly because it takes a while to mitigate and especially to recover. The other two stages are shorter, but still they are as important: preparedness and response. Right. So with that in mind, you know, very quickly, I just want to show you a couple of pictures in terms of what you can do for the power grid, right? before such disasters. This is basically mitigation examples where you do something, when the weather is nice, right? And you don't have an impending hurricane coming. You can also prepare, right? You put resources in places that are critical for an upcoming event. But of course, if you basically have stuff to recover after in the aftermath, you basically try to do your best, right, to repair and go back to normal, right? These are all examples for power grid, right? In a lot of cases, local agencies, state agencies, utilities, companies, even ourselves, right, we have to make some decisions. We have to allocate resources before these kinds of events. So we make decisions, right? What I mean by that is that we have to use some information to make such decisions, right? And over time, right, we invested quite a bit of money and resources to do forecasting better, to make such decisions, right? And if you look at our forecasts over time, right, in the last couple of decades, right? Yes, we have been doing, because of those investments, we have been doing better forecasts. So if you look at the left side is the hurricane accuracy, hurricane forecasting accuracy for the tracks, right? How accurate our tracks are, and the right side is how accurate our intensity categorization is before the hurricane. Especially if you look at the green line, which is the 48 mark, 48 hour before the hurricane, how well we do, right? As you can see, we do reasonably well, and then we have been doing much better over time. So we have better forecasts, right? What does that translate into our decision making, basically, right? If you look at how disasters were costing us in terms of basic fatalities and dollar figures, right? Maybe not so much, right? So ultimately, this is basically grouped, decades like 80s, 90s, 2000s, and 2010s, right? Both the death count and the dollar count for these storms have been going up. And this is normalized, by the way, per storm. So it is not just we have more storms in the 2010s, right? But ultimately, this is per storm death count and the dollar count. And they have been costing us more in terms of lives and property and infrastructure, right? There could be a couple of reasons for this, right? I have a delay for some reason on my side. Let me see. Okay, here we go. There could be a couple of reasons for this. Like I said, one of them could be, well, do we have really more storms or more intense storms? There is some variability from year to year, right? So this is basically the number of hurricanes from the 90s and on. There was a dry period, right? Here from, I think this is 2009 to 2016, dry period for hurricanes, if you will. Right, but otherwise it is quite active. But even then, the number of intense storms has been changing from year to year. That is why the previous figure with the decade aggregation is important, because these kinds of year-to-year variations are smoothed out, right? But still, we see quite active periods every once in a while. For example, this 2004-2005 seasons, or that 2-year period, we had quite a few intense storms, and then last couple of years have been quite active too. All right, so you don't know for sure, what the trend looks. Climate scientists say that these things will get worse over time, which is what the science shows. But ultimately, at least historically, it is a variable trend, basically. All right, so. Yeah, we have better forecasts, right? Thanks to the investment to these kinds of this kind of modeling for advanced forecasting. Of course, we have more up-to-date observation data, higher resolution models, right? Faster computing, right? So that is why we have better forecasts. But how come predictable weather events like hurricanes, they still turn out to be what I call disasters or tragedies, right? And they become really costly. I put some plausible reasons in here, right? Yeah, maybe we have more frequent, more damaging hurricanes than before, and I've shown a couple of slides for those. I didn't show any maps or anything like that, but there is definitely more population and property at risk in the coastal areas, right? But I argue that maybe we are making some of these decisions that are so important, not fully understanding the impact of these events. I don't know, my word is cut off here, but so we don't really understand maybe these events. We don't fully use these forecasts in our decision making. That's basically what I want to argue today, right? And this is especially important if the first two reasons were, if you believe the first two reasons, right? If you believe that there's more, worse storms coming to our way and more population and property at risk, right? Then we should really pay attention to fully understanding the impact of these events and make these decisions, mitigation, preparedness, and recovery decisions much more carefully than before, how we have been doing basically. So with that in mind, for example, you could say, well, I will use that information. I will use forecasting methods. But one of the things that people usually use is these FEMA floodplain maps. Right, this is for Harris County, Houston and surrounding areas. Right, it shows you the 100-year and 500-year floodplain basically. But this is static. It doesn't really work for a specific event because this is really derived from the historical data and how the flooding has been happening in the, let's say, past 100 years or so, right? Typically 160 to 70 years. But ultimately, they say, yeah, these are the places at risk. But ultimately, it doesn't really say much about an impending event that might be coming from left, right, bottom, So you have to be focusing on an event-based risk. If you do that, you can certainly look at the specific hurricane track and rainfall forecast, right? This is both of them for Harvey, right? If you look at the 48-hour forecast for Harvey, right, you can see where the track is and where the cone of uncertainty is and all that, right? You can also see where it's going to rain, right? But these are also these are event specific, which is nice, but it doesn't really tell you where it's going to flood, right? Ultimately, you might say, well, where it rains, it should flood. But my geoscience geoscientist friends, and others, right? They will tell you that flooding is not that simple. It floods even in low rain places because it depends on topology. It depends on elevation. It depends on the river network, how the streams get put together, right? So it is not so simple. So maybe you have to do really what we call you have to take the rain input and potentially other atmospheric inputs, and then you should do what we call rain to flood modeling, right? This is just one example, right? So if you feed the rain data into a model, flood model, then it will give you basically where it's going to flood, right? So which is nice, and you can do this on an event-specific basis, right? But then that's not even enough, I argue, because then you really have to look at the impact of those of that flooding, right? These are basically actual power outages from Harvey, in I guess Corpus Christi and the Houston areas. So you have to basically say, okay, these are the places that are going to flood. But how about my infrastructure? Where do I need to pay attention when I try to gather, my resources to allocate before the storm, right? Where should I pay attention to in my infrastructure, right? So you have to really overlay your assets from your infrastructure onto the flood map, if you will, the actual flood forecast. And then you say, okay, these are the places that I should focus because they could be flooded and whatnot, right? So you can do that, which is like, again, one more step basically in your process, but we still have quite a few difficult choices to make. All right. So when you look at the number of flooded substations, for example, the assets that you may consider as vulnerable, right? And see how many of them you should cover, right? Especially if the hurricane is a major one, right? A number of alternatives, the combination of decisions that you have to consider, right, will be way too many for you to consider by hand or by Excel spreadsheet, for example. All right. So you need another model to be able to contemplate what all this flood impact means. All right. And then we have to really know, how these preparedness, right, before event decisions that I make, and then after event decisions that I make, right, how those two things go together. I have to make such decisions. When I make those decisions have to be coordinated, right? I cannot just do them in a decoupled manner. And finally, maybe as a minor issue in decision making, but ultimately important, the vulnerabilities of our assets are somehow correlated due to the nature of such events, right? The flood or the hurricane impacts an area, and these assets or substations, for example, for the power grid, they don't go just independently. They don't flood independently. You have to look at the whole region to say, oh, by the way, these guys are connected, and they are vulnerable all at the same time because of the flood that is impacting a whole region, right? So I will show you very quickly a couple of slides for each of these points to make my point, basically, right? This is the left side is the Texas grid, power grid, basically. Actually, a made-up one. We don't really know exactly how the power grid is connected, but this is basically a made-up, grid that is on the footprint of Texas, basically. But it represents the real life Texas grid quite well, right? And on the right side, you see an example of what you could do before an event, before flooding, right? These are called tiger dams. You put them around your substations to prevent flooding, right? Up to a certain height, of course, right? So if you look at how many substations that you might have in your system, and this made up thing has has 2,000 of them, right? And of course, not all of them will be vulnerable in a hurricane scenario. But if you're in the Houston area, for example, you might have quite a few that are vulnerable, and then now you have to decide, okay, which ones you should protect, right? If you have enough tiger dams, maybe you are willing to protect all of them, but that's not usually the case. You have a limited number of these guys, and then you want to put them in the most critical places, right? So just as an experiment, right, I basically said, okay, what if I have 100 substations to consider, right, as vulnerable, and then decide, how many I should protect, right? The number of combinations that you should consider is more than 10 to 30, right? Close to the number of atoms in the universe. Not quite, but close, all right? Even if we have our lifetime in front of us and then reserve the Fronteras, the UTs, the new supercomputer at our surface full time, right? We won't be able to finish evaluating them in our lifetime. Let's put it that way. So we have a better way of basically evaluating these options as quickly as possible, so we can make timely decisions. All right. So we don't have that kind of luxury before the event, right? So what we do is, we basically say, okay, yeah, I will consider these options, right, in my decision model, but still, should I just focus on one flood and then, or one input to my model, see where it's going to flood, see where it's going to impact, use it in my decision-making model, consider all options. Even then, I'm not done yet, we believe, because ultimately, the forecast is a forecast, right? So ultimately, we really have, accuracy problems, right? Even if we have the best forecast, we don't have the perfect flood models, right? So somehow we have to consider the fact that the flood not only the weather forecast, but flood forecasts are just forecasts. So we have to really simulate multiple inputs to these models so that we can basically see, what other scenarios are possible before we make our decisions. Typically, what people do, they basically look at the best track, the most likely track from a hurricane. They look at that map, right? They look at the flood impact if they do, but then they don't really consider, or they don't have time to consider other options, right? So what we say is basically, how about we look at all possibilities for the track or intensity and other features of the storm. We simulate them, right? We simulate them through a flood model and see, and serve them as flood scenarios to our decision-making model, right? So this is basically what I call one cone of uncertainty, multiple tracks, right? So using that one cone of uncertainty from the hurricane information, right? We basically say, okay, how about we generate 25 scenarios, 25 different tracks, making landfall at 25 different locations, right? And see their impact, right? Let me see, right? And if you feed every single one of them, right, you will have your flood map basically, and these are basically hospital and nursing home locations in the Houston Galveston area, right? This is actual flood model that we ran to see where it's going to flood, right? And as you can see, this is again for Harvey, right around the late August time, right? It floods quite badly in that region, right? But imagine that we do this for for 25 different tracks, right? The main difference between them is actually, maybe I will show you this. I had one thing in here. Oh, here you go. For some reason, I skipped this one. The main difference between them, right, for such tracks is that we do precipitation shifting. So in a way, this is scenario one, this is middle scenario, I call it, and then this is the last scenario. I didn't want to show you the whole thing, but we have 25 scenarios, right, with the different tracks. At the very least, precipitation where it's going to rain is going to shift, right? And of course, there are other things that are happening when you change the track from one to another, but this is one example that I'm showing for precipitation. And the observed rainfall data is the leftmost map. But as you can see, these tracks carry different kind of information to our flood model, right? We repeat this basically for all 25 scenarios, and then that part is really what I focused on was the inland flooding. We do pretty much the whole thing for coastal flooding, right? Using, in the past we used slush, that was NOAA's storm surge model. But we are now in the process of basically converting everything to EdCirc, which is a much more demanding but better forecasting tool for storm surge. All right. So that part we do, and then we basically say, okay, where did it flood, right? And luckily, our scenarios, our framework is such that we can basically capture the correlated flooding across substations, right? In each scenario, the substations that are basically flooded together, they are captured. So as a side product of this, we basically handle the correlated flooding as part of our process. People use independent, component-based fragility curves for independently analyzing failures or risks of individual components or assets in an infrastructure or a network. Those kinds of tools really lose the big picture because they look at the pieces individually, independently. And these kinds of things really go together, and you have to capture that kind of dependency. All right. And finally, to see the impact of such flooding on our power grid, we really need to model, right? So there is this impact modeling, right? So how the floods are going to impact our power grid, but we also have to look at and see, okay, now in the aftermath, what is my performance, right? How am I going to deal with the situation where I protect what I can protect, right? the other stuff flooded. Now, what is my performance, right? So for that part, you really need another model, power grid model, that basically captures the performance of your infrastructure, basically. All right. Just as an example, right? So the left one is basically, this is a coastal grid that focuses on the Texas coastal area and the power grid there. As you can see, the size is 663 bus network, right? In there, right? Suppose that you can basically supply 40 gigawatts of energy, right, to people there, right, with no problems, right? But then I basically put 8 axes on some random substations, right? Suppose that they are flooded in a scenario, right? Then you are down to 32 gigawatts. So you should be able to measure that impact, right, in your power grid model. And plus, somehow, if you're able to, I don't know if you can see it, but there are a couple of purple ones in here that I fixed, that I protected before the storm. In this scenario, then I'm back to 38, and my models should be able to say that, should be able to evaluate that, and then tell me how well my protections are working. All right? Does it make sense? So ultimately, with that in mind, right? I have to connect these two sides of things, right? Preparedness decisions and recovery decisions in a decision model, and then make my decisions in an optimized fashion, right? This is basically landfall point is our due date, basically, right? Before that, whatever we can do, we'll do it beforehand, right? And after that, we are, the stuff happened already, and then we are in the recovery stage, right? During this time, I call this basically 48 hours before the event, right? Maybe up to 24 hours before the event, we can do certain things. Then that is our basically decision-making time and implementation time, right? We'll make our decisions, right? But ultimately, we'll make our preparedness decisions without knowing exactly which scenario will unfold, right? But then we'll have to deal with we'll have to deal with those decisions, in the recovery, right? So this dependency between the two has to be captured in our decision model, which is what we do basically in our stochastic optimization model, right? We decide what to do, right? What to protect and up to what level of protection, right? Before the event, looking at all 25 scenarios and their impact and their evaluated performances, and then for each of them, we have a contingency in the aftermath for each scenario, right? And all these decisions are coordinated in our framework, which is a nice thing, right? So you're not just decoupling these stages because they are decoupled in time, right? But you're actually considering them all together while you're making critical, important decisions. All right. So what I call is, let's connect the dots, right? Ultimately, we saw that we have the forecast, we have the flood scenarios, we have the impact modeling, right? And of course, we have the decision-making modeling and optimization. Even my team doesn't know this, but I have this new acronym for our approach, right? Integrated Prediction Optimization-Based Decision Support. It's a mouthful when you say it word by word, but it is called IPODS, right? So we try to integrate prediction and optimization, and we put them all together for decision support, all right? And now, this is usually my first slide in my presentations, but ultimately, if I show you this now, it should be all apparent that, oh, by the way, this is all this, I guess this linear representation or presentation, right, is in a U-shape. Since it doesn't fit the slide, right, I basically put it in a U-shaped flow. Forecast, flood modeling, and then the power grid modeling, and then of course optimization to make your decisions. This is basically the whole. And it has some more details because it has we have some nice visuals in there to show you what each of those models do. But ultimately, that's the whole thing for the power grid, right? So before another example, see, for some reason my slides are slow to transition. Okay, here we go. So this is one example result from our grid work, right? This is basically a Tiger Dam problem. If you remember, 25 scenarios for Harvey, and then we look at the amount of demand that we couldn't satisfy because of the flooding, right? And then we try to increase our budget in terms of number of Tiger Dams that we have, that we can deploy before the event, and see how well we do, right? So we have a couple of lines in here, but the most important line is this green line, mainly because that shows what we can do with our tool, right? And if you just use the same tool, but with one scenario, which is the mean path scenario, right? Still optimized decisions, but with mean path scenario, then these down triangles, right? Upside down triangles, the yellow ones, that shows you basically how well you do with that one scenario, right? But still optimized and still using the power grid model. So you save quite a bit of energy, right? Power basically by using our framework as opposed to the mean path, expected path scenario. And of course, the upside, right side up triangles, these guys, that's the lower bound, right? This is the best you could do if you knew what will happen basically in terms of scenarios, all right? Okay, the second example that I want to give you is from healthcare infrastructure, right? We do pretty much the same thing, right? Except now our infrastructure is healthcare, which is basically really hospital networks and nursing homes that we have in the same region that we use. This is still the Houston, Galveston area, right? This is actually motivated by a problem, that was experienced during Harvey. An agency called CETRAC evacuated more than 1,500 patients from 25 plus hospitals and nursing homes before Harvey, just before Harvey, right? And I cannot imagine how they did it, but we have now a tool that basically takes all these different scenarios, all the flooding risks into consideration, and then makes staging area location decisions, right? Where to put our ambulances and medical personnel before the event, and then how we should route those resources to sending hospitals, the impacted hospitals, and then take them to safety or take them to receiving hospitals, basically. So all of those decisions are made together. And just to show you how that is done, again, the same kind of flood modeling, optimization, and of course a map that shows what your decisions are about staging areas and evacuation routes for your patients and nursing home residents. All right. Actually, before you do any of that stuff, flood level analysis is really useful. Using your scenarios. I know this is a little hard to see, but this is basically showing you the hospitals and nursing homes in one column, and then flood risk in the other columns, where you basically say, well, okay, if these are the scenarios, right, and if I believe my flood model, then I can basically see how likely and how much of a flood is likely for each of those locations, right? This is even before optimization and routing of patients. And of course, if you do the routing, right, you can actually capture how you should allocate your budget in terms of your pre-event budget versus total spending. As you can see, if you spend a little bit more, right, in total you spend less, right? And of course, you can basically parameterize it with the storm intensity, right? Sometimes, as you can see in here clearly, that a not so intense storm, an easy storm, may cost you a lot if you are not spending enough money ahead of time, right, to mitigate and to prepare for the event, right? Is it just hurricanes and heavy rainfall events? I'll show you one more example. Right, especially if you guys experienced the February winter storm in here. Resilience to cold weather, is it just for things for people up north? No, it is in Texas too, right? So how do we make sure that our power grid, our water systems and gas supply, right, they hold up to cold weather? All right, this is just a visual of that. for our actual winter storm that we experienced in February. But ultimately, we are basically considering, actually we have a couple of results now that we generate winter storm scenarios. We integrate the same kind of modeling that we talked about, right? And we make optimized winterization decisions. This is basically, I'll show you very quickly, right? So this is basically a sample result from our initial study, where we look at the ERCOT, that is the power grid operator for Texas, right? ERCOT outage data for the February storm, use them to generalize the distribution of generator failures, right, due to weather. And these are basically probability distributions for different regions and different generator types. And then we use them, we generated actually 5,000 scenarios, winter storm scenarios. They're not going to all happen at the same time, of course, right? They will happen over time, but they are Texas-wide storms, similar to ones that we experienced in February and simulated, right? And so basically how we should do, where we should winterize and how that would be changed with increasing budgets, as you can see in here, right? Resilience is not just about impending events, though. This is what I want to highlight as the last point before I finish, because these things happen over time. These resilience management cycles, they happen not just once, they happen multiple times, right? And you have to really basically go, look at your multiple seasons, and actually you have to consider years, decades to make even longer term decisions, right? Just quickly to show you, right? Climate change, right, will impact some of these things that you do. This is the latest summer version of the IPCC report. As you can see in here, they expect much heavier rainfalls, much more frequent rainfall events. They expect more hurricanes and more intense hurricanes, right? So how do we prepare, right? We can do business as usual by basically saying, well, okay, we'll respond to them as best as we could, right? But ultimately, we should ask an even more fundamental or in reverse question, which is basically, how should we design or adapt our infrastructure for these future risks, right, that we haven't really experienced yet, right? We should basically make it, we should develop a strategy, right, transitioning our design and adapt our design for such risks, right? And that is basically what I want to finish with. We are in the process of developing such long-term models for the power grid, but ultimately we have very much more questions to answer when it comes to our own work. Other infrastructures, like I said, supply chains. This is just one example in here, where on one day, you have your supplier impacted, next day your manufacturer, next day your distributor, and then before you know it, your retailers are out of stock. We are actually experiencing a supply chain issues as we speak, right, due to COVID. But these kinds of things, these weather events impact supply chains too. Water systems, interdependencies between infrastructures, right? We saw how it's unfolded during the February storm between power grid and water systems, and between power grid and the natural gas supply. Just want to show you that I haven't done any of these things by myself. It's all about teamwork, right? I have colleagues in geosciences, electrical engineering, OR, which is my field, of course, and Energy Institute. Very many capable students, some former or old, right? These are PhD students who graduated in the past year, and then some new and some current students that are helping us do all this work. And this is a picture from our weekly Zoom sessions. You see everybody is smiling. And then more sponsors and collaborators. I acknowledge the support from Energy Institute, Planet Texas, and NSF, and Sandia. And of course, we have more collaborators, as I have said before. All right. Thank you.
Thank you so much, Dr. Kutanolu. It's been a very interesting presentation, and we've had some questions in, so I'll start reading some of them.
Sure.
So one of the questions that came early on is about why not building the power substations at higher elevation in the first place? And that maybe you can comment a little bit about how your work can inform future positioning of some of these critical infrastructure structures.
Yes, definitely. Right. I show you early on. It's a very in the back, but ultimately, yes, elevation, right? Increasing the elevation of these substations is a good way. And let me see. Yeah, and definitely our tools could help for those, because ultimately, especially, I skipped that slide, but if here you go. You could potentially simulate many storms, right? And because ultimately, when you mitigate, right, you're not just trying to protect for one event. You're protecting for a variety of events that might come your way, right? In this, for example, these guys are representing the tracks of pretty much close to 500 storms. You could simulate, these storms, right? You don't know which one is going to happen and when and whatnot, but you basically simulate and then see where it's going to flood and where your critical infrastructure is, or where you think that you're going to expand your power grid, and basically you put your at least new substations at higher grounds, right? If you think that there is a new flood risk, right? The FEMA maps show basically the old flood risk, right? But by basically simulating and using these higher resolution tools, event-specific tools in an aggregated, in a basically brute force way, you can look at the overall risk, future risk of these storms, and then decide, where you should really, basically use higher ground substations. Yes, definitely, that is something that you can use it for, and that is why actually, of course the event-based decision making is important, right? Because it's going to happen in the next couple of days, but we should take these longer-term decisions as seriously, because ultimately we have the luxury of time, right? Because the event is not pressuring us, and we have to capture the risk correctly, though. Otherwise, we might just say, "Oh, it's not going to happen. It's going to happen every 10 years or 100 years. Let's not worry about it." But then it happens, right? Things happen, and then we have to deal with the aftermath, and then we spend hundreds of billions of dollars in the aftermath. So capturing that risk carefully for longer term decisions and spending where it needs to be spent using our models is the way to go.
Great, thank you. Now, the last decade, can you comment how much has improvement in computers or processing helped in better prediction compared to improvement due to better theoretical understanding and equations?
Yeah, there is some work, right, by geoscientists and others that basically look at the improvement in forecasting accuracy for such models. I'm not an expert. I basically grab a couple of charts here and there to show you that, yeah, it is getting better. We are getting better overall as a society when we invest such money for forecasting. But we all know that computing has improved, right? So ultimately, we have now pretty much an old school, a supercomputer in our pockets now. Back in the 70s and 80s, people would think that our phones are supercomputer, but ultimately we are aware of that. But how much, if you compartmentalize the improvement due to computing improvement, due to physical modeling, or due to up-to-date data because of satellites and whatnot, I don't know if anybody has worked and figured out, yeah, this much, 10% improvement is for this, and 20% of improvement for that. I'm not aware of such study, but there could be one that I don't know. But they are all important elements of how we do better and better in terms of forecasting over time.
Great, thank you. Well, Dr. Erhan, you touched a little bit on the supply chain as a potential area for the future. There were some questions around that. Can you comment on any work that you have done already, or perhaps how can our audience, companies, industry, organizations collaborate with you on the supply chain aspect?
Sure. Yeah. Well, yes. So in my previous life, let's say, right, before I started dealing with the disaster and humanitarian logistics and disaster decision making, actually, I worked on supply chain problems, logistics problems, for all kinds of companies in all kinds of industries. But I wasn't dealing with the disasters and whatnot at the time. So we were trying to maximize basically profit and of course coordinate decisions, in a plant or across a supply chain, with transportation options and whatnot, right? So, but I can clearly see that yes, the vulnerabilities of the supply chain can be modeled, right, as in a network, and we can analyze such problems in the same way that we analyze in here, in basically in a societal problem, let's say. But if you ask me whether I have worked on such a problem, not yet, right? So I know, companies like Walmart and others, they are interested in such issues because they deal with, all of these companies, right? Refineries and chemical plants in the Gulf, for example, right? They are subjected to such risks. In the Northeast, we saw that how the remnants of, even Ida impacted a very much dense populated place and impacted the supply chain, right? Now our ports are impacted in a different way due to our capacity problems, right? But ultimately, all of these things are showing basically the need for integrated prediction and optimization when it comes to decision making, because you cannot just look at a map and say, well, yeah, I have issues in the ports, right, in LA, and now I have to make this such and such decision, because that's not it's not trivial. You have to really look at the whole thing, the interdependencies between and correlations between your risks and decisions, and then look at them as a whole, and then do it. And I'm open to if they reach out to me, right, here at this email address with a short introduction, I can get back to them, and then we can start talking when it comes to collaboration, because those are the problems that I knew even before I knew about hurricanes and the cone of uncertainty and whatnot. So I'm quite familiar with the domain.
Great, thank you. Mm-hmm. Here's another question. Is the challenge of understanding how to make the infrastructure more resilient mostly a matter of modeling complex systems interactions, or getting good predictions of potential failures, or both?
I think both. As I tried to argue, right, evaluating these things and modeling all these interconnected decisions and network infrastructure and whatnot, it's not easy, right? My students will tell you that, oh yeah, Dr. K, I have been running this for 2 hours and still I have quite a bit of gap between. We basically look at how close we are to the optimal solution. We look at this gap, right? And then they say, oh, by the way, I'm 15% away from the optimum. And I say, no, we have to run a little longer and then see really where the true optimum is for these decisions. And by the way, we are not really solving toy problems, right? Even our coastal problem has 660 bus grid. It is not test grids basically, right? So ultimately, that's a challenge, right? Modeling and computing is a challenge for these decision-making problems, but we have to do it. We cannot just say, oh, I don't want to solve it because it takes too long or too hard or whatnot, right? but predictions matter, right? So forecasting accuracy and prediction accuracy, they matter quite a bit too, right? One good thing about our models is this though, right? If we think that we are going to have better forecasts, better predictions in the future, right, through better physical modeling or better, my team is working on machine learning models now to combine physics-based model with some data intensive methods like machine learning, and then we basically hopefully do better predictions, right, in the future. You can basically see the impact of such improvements using our models too, because now you're dealing with a better set of scenarios, right? And or lower variability scenarios, right? And you will be able to make even better decisions just because of that. And you can see how much the delta is. Now you'll be able to save even more power. You will be able to save even more lives and property because you have better predictions, and you can quantify how much the improvement will be.
Great. Yep, makes sense. So we are going to have to start wrapping up. I'll ask the last question here.
Sure.
And people are interested in understanding, is there some papers or written information? Where could our audience find out more about your work and your students?
Yeah, so if they remember my last name, right, and then Google it, there is not very many Kutanoğlu's in the world. So they'll find my webpage and my papers. I have a Google Scholar page and whatnot. But ultimately, we also have I didn't put the website in here, but sites, .utexas.edu/Erhan, my first name. That's my website. Yeah. You see, I'm not good at marketing, so I should have put my website in here. Just put the email address, but yeah, this is my website, and then you can just go in there, and then in the worst case, just reach out to me, and then I will share what I have.
Great, thank you so much, Dr. Kutanoğlu. We really appreciate the time and the topic that you share with us today. It was my pleasure to moderate the talk, and now I will hand it over to Canavis to wrap it up.
Thank you so much, Eloisa. Hello again. My name is Canavis Smith, and I wanted to formally thank each of you for joining today's webinar, and we hope the conversation was valuable. If you would like to learn more about future webinars or to hear more about hot topics that are changing the industry, please be sure to follow us on our social media channels. Next, we wanted to thank the 3 units of the Cockrell School of Engineering that helped put this wonderful program together. First is the Texas Engineering Executive Education, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is our Petroleum Extension of Texas, or PTEX. This department has been around for over 75 years, serving the oil and gas professionals with skills training, either through e-learning, publications, and online and in-person training. We have the training to meet your energy-related needs. And last but not least is our research relations team. This team partners with industry to solve some of the world's biggest problems in energy, water, transportation, disaster analytics, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT researchers. If your company would like to partner with the university to explore additional research opportunities, please email the Research Relations Office to initiate a discovery discussion. All 3 units are here to serve you and your company to help you reach your full potential. So if you would like to provide feedback on today's webinar or to learn more about receiving CEUs, make sure you complete the evaluation survey in the chat or in your email following this presentation. Once again, we would like to thank you for joining us today. We hope you have a great weekend, and hook 'em horns.